In this video, we solve problem 11.1.077 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're told that three forces of magnitudes of 55 pounds, 109 pounds, and 149 pounds act on an object at angles of 30 degrees, 45 degrees, and 120 degrees, respectively, with the positive x-axis. We're asked to then find the direction and magnitude of the resultant force. So the first thing that I would suggest we do is just sketch these forces and imagine that the object that these forces are acting on is just sitting here at the origin. So I've got one force with a magnitude of 55 pounds, and that is at an angle of 30 degrees with the horizontal, so with the positive x-axis. So I will draw a little force vector here, and I'll say that that's F1, and we know that the magnitude of that is 55 pounds, and that angle there is 30 degrees. Now the next force has a magnitude of 109 pounds. Now it's not exactly twice the magnitude of the original force, but it's close to twice the magnitude of that first force. So I'm just going to try to draw it twice as long as this force that I drew over here. This isn't exact. My angle is probably not exactly 30 degrees, but by drawing it close to accurately, we can get a better sense of what's going on. So for our second force, we've got a magnitude of 109 pounds, and the angle that this force makes with the positive x-axis is 45 degrees. So I want it to be twice as long, but at a 45-degree angle. So I'll draw that. I'll call that F2. And we'll just call this one theta 1 equals 30 degrees, and theta 2 equals 45 degrees. That's what that angle is right there. Okay, and then our third force is 149 pounds. So it's a little bit less than 3 times that first force in magnitude. And it makes an angle of 120 degrees with the positive x-axis. We know from here to here is 180, and 2/3 of that is going to be that 120. So, so imagine like splitting this into 3 equal pieces and then trying to go in that direction. And we want the force to be like 3 times that length. It's not perfect, but hopefully it gives us the right idea. And that angle there is 120. Now, if that's 120, the reference angle over here is 180 minus 120, or 60 degrees. So you can use the 120-degree angle if you choose to, or you can use the reference angle of 60 degrees. Either one is fine. Now we've got all 3 of these forces acting on some object here. The question is, what force does that object experience if it's got one force with a certain magnitude pulling one way, another force with another magnitude pulling this way, and then a third force with nearly 3 times the magnitude of that first one going that way? The question is, well, what's the result of that? Well, the way we can find that resultant force is to write each of these 3 forces in component form and then just add component by component. Then we'll have the resultant force in component form. We're not actually asked for that though. We're asked for the direction and magnitude of that force. But once we have it in component form, we can find its magnitude, and then we can use a little trig to find the direction. Now it's helpful to think about just a generic vector in the plane and how that would relate to these angles here. Let's say our generic vector v is making an angle theta with the positive x-axis. Well, I can split this vector v into 2 pieces. One piece that is parallel to the x-axis, and another part or piece that is parallel to the y-axis. And that's going to be the x component of v, and that'll be the y component of v. This will be the x component times I hat. Normally we call that V1. And then this will be the Y component, which we typically call V2 times J hat. So this is for the vector that is given by V1 and V2 in component form. The question is, well, how do we find the magnitude of V1, or excuse me, that number V1 or that number V2 if we know the magnitude of the vector V and we also know this angle? So let's say we're given the magnitude of V and theta, we might want to find V1 and V2. Find that adjacent side, that side that's adjacent to theta. It's not the hypotenuse, it's the other one. Or the side that's opposite theta, it's not the hypotenuse. Well, you can just use a little trig to figure that out. Now, if I'm just thinking about the magnitudes, the magnitude of this piece doesn't include the I hat. If this is 3 times I hat, it's 3 units long. If this was 4 times J hat, it would be 4 units long. And that would make this 5 units long because it would be a 3, 4, 5 triangle, and that's pointing out in this direction. So if I'm trying to find V, I can use just right triangle trig. Since this is the adjacent side of the triangle, I would use the cosine function. We know that the cosine of that angle is the adjacent side over the hypotenuse from right triangle trig. The adjacent side has, I want to say magnitude, but it's really a length, or it's a directed length. If it was going the other way, that V1 might be negative. You just take the adjacent side and you divide by the hypotenuse, which is the magnitude of V. So that means if I want to solve for V1, the adjacent side is the magnitude of V times cosine of theta. And similarly, to find the magnitude of V2, since that side is opposite theta in our triangle, I keep saying the magnitude of V2. Basically, I'm trying to find the value of V2. You know, from right triangle trig, SOHCAHTOA. Remember that guy? That little mnemonic device. Sine is opposite over hypotenuse. The opposite side has a value of V2 when the hypotenuse is given by the magnitude of V. So if we were solving for V2, which is the opposite side, we get V2 as the magnitude of V times sine of theta. So V can be written this way. Its x component, this piece, is the magnitude of V times cosine of theta, and its y component is the magnitude of V times sine of theta. So I've got this picture, but I could also have drawn this picture. Here's V. This side has length magnitude of V times cosine of theta. And that's assuming that theta is an acute angle. If it was obtuse, that would still work. That cosine would just be negative in that case. But we have that times I hat to give us that vector there. And for the opposite side, we've got the magnitude of V times sine of theta. And that's the numerical coefficient there. We're going to multiply that by J hat. This times I hat plus this times J hat gives us that vector V over there. Easy breezy. Okay, so with that in mind, we've got all 3 magnitudes and we've got all 3 angles. If we want to, we could use the reference angle for F3, but we don't have to. I think it's probably easiest to write each of these in component forms using this and then just add component by component to find the resultant vector. Because remember from physics, the sum of the forces acting on an object is equal to that resultant force. So that's what we're using right here. Okay. So let's do the computation. This first force had a magnitude of 55 pounds. We had 55 times cosine of that angle with the horizontal with the positive x-axis, which was 30. And the y component looks just like that, but rather than a cosine, you have a sine. And for the second force, you've got 109. That's its magnitude, 109 pounds times the cosine of the angle that force makes with the positive x-axis, which is 45. And the y component looks the same, but it just has a sine function. And the same is true for the last guy. Its magnitude is 149 pounds. And the angle that we make with the positive x-axis is 120. Oops, we'll have a sine function over here. Now you don't have to use this 120 if you don't want to. If you want, you can just take this force F3 and split it into two components this way. Got one component that's going in the negative x direction. That would have a magnitude, or it would be given by, excuse me, the magnitude of that force times the cosine of 60, because that's our reference angle. That's what that length would be, but it would be pointed in the opposite direction. So we'd put a negative sign on that. So rather than writing this 149 cosine of 120, if we wanted, we could write negative 149 cosine of 60, but negative cosine of 60 is the same as cosine of 120. So it's up to you. You can do it this way, which is simpler as far as the computation is concerned. But when I'm thinking about the physics, I really prefer this way, where I look at that reference angle and say, well, these forces are actually pulling to the right. This force is pulling to the left. And the magnitude with which it pulls to the left is that 149 pounds times the cosine of 60. And then we see that the y component is positive, and so we'd have the magnitude of F3, which is 149 times sine of 60, which happens to be the same as the sine of 120. Okay, so we just add these three guys together. And that's going to give us our resultant force. I'll just abbreviate that F sub R. And I will use decimal approximations here. Now, we were asked to find the direction and magnitude of the resultant force. And if we look at WebAssign, we see that they want the direction as an angle in degrees. And it's an angle from the positive x-axis again. And then they also want the magnitude as a force in pounds. And they want us to round both of those to one decimal place. Since I'm rounding that to one decimal place, I think I'm just going to keep 2 or 3 decimal places on each of these guys. Just to make it slightly more accurate. So we'll just find these 3 components, add them together. So I've got 55 cosine of 30, make sure you're in degree mode, plus 109 cosine of 45. If you remember the values of those trig functions evaluated at your special angles, that's great. I actually don't have those memorized. I actually just have a couple of triangles memorized, and I would draw the triangle and use the triangle to infer those guys. But if I want a decimal approximation out to 3 decimal places, I'll use this 50.206. That's a number of pounds of force pulling to the right. And of course, it's an approximation. And this is a number of pounds of force pulling up or down. I think it's going to pull up because all of those forces have components that are positive. They go in the positive y direction. They're all pulling up. With these guys, we had these guys, these 2 are pulling to the right. This one was pulling to the right or to the left. So net, we ended up with a force of 50 pounds, 50.206 pounds approximately, pulling to the right. So now this is going to pull up. So let's see what we get when we do that. So we'll have 55 sine of 30 plus 109 sine of 45 plus 149 sine of 120. Close parentheses. And looks like we've got 233.612 pounds of force approximately pulling up. Okay, Now that's not what they asked us for. They asked us for the direction and magnitude of this guy. So for the direction, it's helpful to draw a picture again. I've got approximately 50 pounds of force going this way. And I've got approximately 233.612 pounds of force going this way. Of course, it's not to scale. And you add those two forces together. Oops, just make it longer. There we go. And you get your resultant force. So if I want that angle, that direction angle measured from the positive x-axis, I will just use the tangent function. I've got the length of the opposite side and the length of the adjacent side relative to that angle theta. So tangent of theta is this y value over that x value. Just take the inverse tangent of that and you'll get your theta. So I already have this y component in my calculator, so I'll use that. And then I will divide it by this 50.206 that equals. And then we'll do inverse tangent of that answer. Oops. I'm going to delete that, just answer, close parentheses, hit equals, and my angle theta is approximately 77.87 or 77.9 degrees. And hopefully we rounded in the same way that the people who created the key on WebAssign rounded. And hopefully they have exactly 77.9 degrees as their approximation as well. All right, now we just need to find the magnitude. We know the magnitude of the y component and the x component. You've got the two components. Remember how we find a magnitude? You just take the components, you square them and add them and take the square root. So we'll do, and of course this is an approximation as well. X component, square it, add the y component, squared, and take the square root of that result. And of course, we're getting an approximation again. And square root of your answer, and we get 238.9 approximately. And all of those measurements were in pounds. Okay, so that's how we do that. Just write the forces in component form, add component by component, just find the magnitude and then use a little trig to find the angle. Let me know if you have any questions about that.